Okay, so today we are going to start Unit 6. And if you all remember, back at the beginning of the year, I talked about calculus. AB has three big topics or three main ideas, and they were limits, derivatives, and integrals. And so Unit 6 begins integrals. And today we aren't going to actually talk about that word and what it means, but we are going to start using integrals without really knowing what they are. And so before today, most of the time when I'm like, what do we need to find? Your answer has always been the derivative. So starting today, we still might need to find the derivative, but it's possible the answer to that question is going to start being something different. So that's good. You guys get to learn a whole new idea. All right. So on this activity, the question is how much snow is on Jane's driveway? So the weather forecast for January is a snowy one. At midnight, there are 80 cubic feet of snow on Janet's driveway. Snow accumulates at a rate of 50 cubic feet per hour. At 6 a.m., Janet wakes up and starts shoveling. Will she be able to make it out of her driveway in time? So the first question asks how much snow is on Janet's driveway at 6 a.m. So that needs to be the amount of snow there is at midnight, and then how much accumulates between midnight and 6 a.m. So at midnight, there's 80 cubic feet. And then it snows at 50 cubic feet per hour for 6 hours between midnight and 6. So that is going to be 380 cubic feet. All right, now I started number 2A for you. So between 6 a.m. and 7 a.m., Janet shovels snow at a rate of 125 cubic feet per hour. And then she gets a little tired and slows down. So between 7 and 9 a.m., Janet shovels snow at a rate of 108 cubic feet per hour. And we're going to write a piecewise function for S prime between 0 and 9 that gives the rate of change of the volume of snow in Janet's driveway T hours after midnight. So I went ahead and I did the middle one because what I know is that it's snowing at a rate of 50 cubic feet per hour, but she's shoveling at a rate of 125 cubic feet per hour. So that negative 75 is 50 minus 125 because she's shoveling out faster than it's snowing. So we have a negative right there. All right, so what I want you guys to do is number 2. I want you to fill in the rate the snow is changing, the volume of snow is changing in her driveway between 0 and 6, and the rate at which snow is changing between 7 and 9. And then we're going to do a graph of that piecewise function. So pause the video and do that. All right, and then the graphs of these are horizontal lines. So between 0 and 6, we have a horizontal line at 50 cubic feet per hour. And then I'll put an open circle at 6 because at 6 o'clock she starts shoveling, and then the rate is negative 75. So between 6 and 7, it should be a horizontal line at negative 75. And the open circle at 7. All right, and then between 7 and 9, we should have a horizontal line at negative 58. Okay, so I want you guys to think about number 3 for a second. When is the amount of snow on Janet's driveway decreasing? So remember that we have a graph of a derivative, and a derivative, when a derivative is negative, the original graph is decreasing. So the amount of snow should be decreasing between 6 a.m. and 9 a.m. because she's shoveling faster than it's snowing. But the calculus reason is that S prime is negative. All right, and then 80. How much snow is on Janet's driveway at 7 a.m.? So we've already done this for 6 a.m. So it's going to be that same thing. At midnight, there was 80 cubic feet, and then it snowed 50 cubic feet per hour for 6 hours. All right, and now between 6 and 7, the rate is negative 75, so it would be minus 75 for 1 hour. And that's going to be 305 cubic feet. Now, I want to show you how you can do this with a graph and using areas instead of using that. So if I made a rectangle here that's between the x-axis and the derivative graph. All right, let me make it a different color, sorry. All right, and then another one here. My lines aren't perfect. And then that's between 0 and 7. All right. So if I wanted to find the area of that big rectangle, I would do the base times the height, which is going to be 50 times 6, or 300 is that area. And then same thing for this, the second rectangle, base times height is going to be 75 times 1, or 75. All right. So what you can do instead of what we did is find those areas and add them and subtract them. So an area of a rectangle above the x-axis is going to be a positive one you would add, and then an area below the x-axis is going to be a negative or one that you would subtract. All right. So I want you guys to do number 5 on your own. So we're going to find the amount of snow in her driveway at 8:30, so halfway between 8 and 9. So find the area of that one. Decide if you would add or subtract it to the area we just found. Okay, so the area of that one should be 87. So we would take that area we just found and subtract that from it. And we could go back and do 80 plus minus and then another minus, or go ahead and just use the one we already found since we're accumulating. All right, so let's fill in some important ideas. All right, so an accumulated quantity, the way we did it the first time, we did rate 1 times the change in time 1, and then plus rate 2 times our change in time 2. All right, and we would just keep doing that for however many rates and changes in time we have. So we'll say rate N times change in time, N. All right, so the accumulation of a quantity is represented by the area underneath its derivative graph. All right, or derivative curve. So if we're wanting to add up SNP or we're wanting to add up distance or whatever, we can find the areas under the derivative curve and it will give us that. Now, one thing we do need to know is the units. So on this one, our unit for the derivative curve was cubic feet per hour. And then when we added our areas, we got cubic feet. Because what we did is we multiplied that cubic feet per hour by hours. So that's what we're going to do for the units. For the area underneath the rate of change curve, it's going to be the units of the rate of change multiplied by the units of the independent variable. It says independent variable. So that's just the opposite of what we did when we were doing the derivative. When we were doing the derivative, we would divide. When we're doing the area, accumulating areas, which and eventually it's going to be integrals, you multiply. Right, and then one last thing, the area above the x-axis is a positive area. So it's going to be positive accumulation. And the quantity is going to be increasing. And then the area below the x-axis is a negative area or a negative accumulation. And the quantity is going to be decreasing. All right, so on example 1, a squirrel starts at building A at time t equals 0, travels along a straight wire connected to building B for 0 to 18, I don't know what the time unit, minutes. The squirrel's velocity is modeled by the piecewise linear function below, where v of t is in meters